Hi, everyone. Let's get this last session started. Woo! My name is Lisa Bucci. You heard me earlier. I'm from the National Hurricane Center. I'm joined by Chris Lancy, my colleague, who will be co-chairing this session. And we are here to talk about the impacts of Recon data, something near and dear to my heart, on TC forecasts. So first up, we have Jason Sipple, looking at taking a preliminary look at Recon impact in HAFS.
Excellent. Okay, thank you, Lisa. So this is not something I originally intended to show at this meeting. I was going to show something entirely different, but I kind of got pulled into it for a number of reasons. One being what's shown here. This is the reconnaissance data that went into the first cycle of the P3 going into Lee. So all those blue dots are TDR. This is from HWRF. HAFS looks similar. This is the data that was assimilated. That's TDR data, SANS, flight level data, and whatnot. You'll see the next slide. We want this data to have positive impacts, and the analysis that came out of this looks kind of ugly. And so that was one of the motivations. I'll show you that in just a second. But briefly, the outline, we're going to go through a case summary of all the storms, look at some overall results, do a comparison between the two HAFS versions, check for problems, then I'll give a summary. So this is really meant to be a preliminary analysis, not super in-depth, but we can glean some things from it. So here it is. Here's the analysis. It's ugly. This doesn't, I guess it looks like a hurricane, but it also has some weird looking stuff going on. There's this huge lopsided area of category 3 winds on the west side. And if you look closely, these are supposed to be isobars, and you can see lobes of low pressure, various locations. I actually got questions from HSU and from Levi about this, saying what in the world is going on with HAFS. And this isn't the only cycle. This is one of many that kind of look like this for Lee. It's happened a few other times. It's actually a well-known problem when you assimilate intercore data with the global error covariance, which is what we do in HAFS. You can get kind of crazy stuff like this. So it's been documented before in peer review. The OU group has shown it. So I was curious if this bad-looking analysis was producing bad forecasts. And so that was one of the reasons why I have done this. There's also been questions from HSU in general. You know, I've done a lot of work with HWRF on the impact of the Recon data in HWRF, and they want to know, hey, is the data benefiting HAFS like it did HWRF? So I've had those questions a number of times. Congress wants to know the value of the planes. We always get this. The aircraft recap plan is an ongoing thing, and we're constantly fielding questions from Congress about the value of this data. And so it's helpful to have cases to show them. There's ongoing OSE work by others, including Sarah Ditchik for the HOT. Some of her results kind of pushed me in this direction as well. And finally, we've never had the capability to compare two different hurricane models, the impact of the intercore data. Previously, we only had HWRF, that was it. And now we have two different versions of HAFS that have this. So it's interesting to compare, and maybe we can learn a few things from that. Here, this is just going to be preliminary, but I think, going forward, I think it'll be helpful to have that. So here's my case summary. These are the cases. Franklin, Lee, Philippe, Tammy. Idalia is running right now, so I haven't included it. It's about 100 cycles, not a big sample, but there's a whole mix of cases in there. A lot of weak tropical storms, some major hurricane cycles, RI, weakening, a whole mix. The green stars show you where Recon began. So it's kind of down here in the MDR, Southwest Atlantic, and then the ending on various locations. I only ran cycles. I'm only assessing between the green stars and the orange stars. So only cases where we actually, in the periods where we had reconnaissance data. Scorecards. All right, so you're going to see a lot of this. generally speaking, without going into a massive detail on this, what we have here is charts that show on the x-axis forecast hour, on the y-axis you have track, the intensity, Pmin and Vmax, and then the different measures of wind radii that are verified. And in general, green is good. That means the reconnaissance is consistently improving the forecast in the sample for example, at this lead time, 24 hours for track. Within the whole sample, you see consistent improvement if it's dark green. Dark brown, consistent degradation. So you want to see a lot more green than brown, okay? And what else is important? Oh, if you see a long stripe of dark green like this, that typically means that the improvement is larger than if you see kind of scatter results. And so that's kind of a general description of what these charts look like. I'll go more into some of the individual metrics later on. Bottom line is you want to see a lot of green. We see a whole lot of green in HAFS B. We see positive impacts generally in both versions of HAFS, but more positive in HAFS B than HAFS A. I'll talk more about that later on. In fact, I'll talk about it a little bit on this slide. So if you look just at Vmax, you can see here's HAFS B, HAFS A on the left, HAFS B on the right. And so this is the MAE. Without Recon is purple, with Recon is green. And then I have the skill on the bottom, right? So you want to be in the positive territory. Both HAFS A and HAFS B both generally have positive impacts from data. You're in the positive territory. Again, the HAFS B is generally much more positive, up near 17% on general average skill with the data compared to without. That's actually a pretty big number, a little bit bigger than we've seen with HWRF. So that's really encouraging. HAFS A not quite as big, around 7%, but still generally a good result. The track, now this is something that's really interesting, that the track improves so much. We didn't see this as much with HWRF, but it's actually a very big impact. With HAFS B, up around 15%. Really, every lead time is between 10 and 20. Again, HAFS A, not quite as big, but still always in positive territory. So that's encouraging to see. It's also interesting to compare weak versus strong cycles. Stan just actually mentioned this at the end of last session. So weak, we're going to talk about the extremes, tropical storms versus major hurricanes. And in the past, we have seen that, for example, HWRF improved tropical storms a little bit more than the stronger storms. We see kind of similar tendencies in HAFS. For HAFS A, for example, you see a little bit more green here for Vmax and Pmin for tropical storms. Then on the right, for major hurricanes, you definitely don't see as much green. It's kind of neutral-ish looking. Track, though, importantly, is positive impact for HAFS A in both ends of the spectrum. So if you compare to HWRF, this is actually better, like I said, impact on track than in HWRF. Previously in HWRF, the reconnaissance data it's kind of neutral-ish on track, maybe a slight positive result. So that's encouraging to see that we're having a much more profound impact on track. The intensity varies, so it's better for weak storms. We're seeing a more positive result for weak storms than HWRF did, but we're not as good for strong storms, which maybe isn't so surprising since we're using global covariance for a hurricane. That's maybe, that's not really the best thing to do. HAFS B, it's kind of a similar story, although it's just more green, right? We're more in the positive direction, but the trends are similar. For tropical storms, we have more green than for major hurricanes. So we got a lot of green here in Vmax, not as much here for major hurricanes, but track is kind of similar for both. We have long stretches of dark green. Again, better impact than track for HWRF, but for intensity, it's better for weak storms than HWRF was. Not quite as good for strong storms. Even here in HAFS B, where we have this positive impact at shorter lead times for the major hurricanes, HWRF actually had a better impact than the reconnaissance data had a better impact than in HAFS B. Okay, next slide.
Yeah, 5 minutes.
Okay, thanks. So it's also interesting to compare the two, HAFS A and HAFS B, and this is actually where we begin to understand where the differences are coming from. So This is for tropical storms. This is where the big differences between the two models are. You can see a whole lot of green here in HAFS B, still green in HAFS A, but not as much. One of the things that could be going on here that I'm strongly suspicious of is that HAFS B starts cycling the vortex from the previous first guess at 40 knots. So when you get to 40 knots, you're using a HAFS B 6-hour forecast. And HAFS A, that doesn't start to 50 knots. So between 40 and 50 knots, HAFS A is using GFS as the first guess, whereas HAFS B is using its own forecast. So I think there's a tendency, there's a capability to build up the impact of this data in HAFS B at these lower intensities and not as much in HAFS A. One area this impacts is the intensity biases. So you can see again green with the data, that's control, purple without the data. HAFS B is on the right, HAFS A is on the left. You can see that in HAFS B, it's kind of neutral on the intensity bias when we have the data, but when we take it out, HAFS B wants to be strong, and you get these really big positive biases. HAFS A has a little bit of this tendency, but it doesn't jump up as much. So again, I think this is likely a reflection of, these are, let's see, this is for tropical storms. Sorry, I'm only verifying tropical storms in this sample. I think a lot of this is a reflection of that cycling. Could be some physics in there too, so I'm not going to rule that out. Looking for problems, one of the issues we've seen in the past using global covariance is that you might see some spin down when assimilating intercore data in major hurricanes. I definitely wanted to look at that. Is the spin down worse when we have the data versus when we don't? And actually, in both cases, the answer is no. So the purple and green lines, they both have a little bit of spin down in them, but it's not substantially worse with the data versus without. Maybe a little bit in HAFS B, but I wouldn't call this a major issue. In fact, the bias is still substantially improved in HAFS B compared to when you don't have the data. Where you do begin to see a little bit more of a problem with spin down is when you have intensity change going on, when storms are intensifying at the analysis time. Then that green line, when you have the data versus where you don't, is more negative in both versions of HAFS. Interestingly, it doesn't really impact the Vmax MAE here in HAFS B. It does in HAFS A. So it makes the MAE a little bit worse. If you go back to these charts, where we're again having lead times and different verification metrics, you look at Vmax in intensifying cases in HAFS A, and it's degraded. In HAFS B, it's not when you add the Recon data. All the other metrics look okay, right? So this isn't a major problem, even for intensifying storms. It's mostly positive results. So in summary, this really preliminary assessment reveals the impacts are mostly positive from the reconnaissance data in HAFS. They're much more positive in HAFS B, driven mostly by the tropical storms. It could be a result of differences in vortex cycling. The data improves weaker storms more than stronger storms. And we have no major problems for strong and intensifying storms, but the intensity impact for hurricanes is not as positive as it was for HWRF. And again, I think that's probably a reflection of the fact that HWRF, we did a lot of work on the DA system to improve the results for hurricanes, and we just haven't done that yet for HAFS. And one little bonus slide. This is HAFS B with and without Recon. So on the left, whoops, go back. Left is with, this is without, and you can see very large differences in the tracks between the two. This looks like GFS, really. I suspect these are very strong simulations going off to the right, and this is much improved. So that's all I have. I guess, yeah, this is for Philippe, right? This is, everybody's been complaining about Philippe. So here you go. I just got this result this morning. Sarah Ditcher gave this to me. So, yay, Sarah.
Okay. Yep.
Yeah, that's what I thought.
We're doing questions at the end. So next up, we have Ryan Torn from University of Albany talking to us about ensemble-based sensitivity guidance for reducing TC track forecast uncertainty. Ryan, can you hear us?
Yes, can you hear me?
Yes, we can.
Thank you. First of all, I just want to say I really regret that I couldn't be there in person. My wife had got jury duty this week, and so I had to stay in Albany to deal with that. And then fortunately she got out of it. So really regret that I'm not there. So I'm just going to provide a bit of a summary of the the targeting methodology that was developed as previous JHT project, and some of the more recent work that I've been doing looking at a climatology of what that looks like. And so if you want to go to the next slide, please. To this group, I don't have to make the argument that, you know, we only have so many resources to do reconnaissance. And so we really need to know, where do we go take observations that are going to have our biggest bang for the buck on a forecast? And that's where sensitivity analysis comes in. And so NHC has had a methodology for doing this that was developed more than 20 years ago. It was based on steering flow, standard deviation, but that doesn't always tell you that the regions of uncertainty in the steering flow are going to have the biggest impact on the actual track forecast. And so if you want to go to the next slide, please. The goal is here to use another ensemble-based technique, such as the ensemble-based sensitivity method, to develop track forecast sensitivities. And so this has been ongoing. This is work that started back in 2015 with the Shout Field program. We first started doing this in real time. And then it continued with informal collaboration with NHC starting in 2017, and then more formally in 2019 through a JHT project. And so my goal here is to talk about how to use this method and how it is used for track forecast targeting, which has been used by the Hurricane Center since 2019. Next slide, please. So this is using the ensemble-based sensitivity technique, which probably many in this room have heard from me before. It is basically just a linear regression technique using ensemble forecasts as the individual samples. Here, the outcome, the dependent variable is your forecast outcome, and this is some measure of the tropical cyclone track that I'll talk about in a second. And your independent variable is the ensemble estimate of some state variable that you want to compute the sensitivity to, whether that be some measure of the steering flow, whether that be in the wind components or the vorticity, could be potential vorticity, could be height, whatever you want to be. And so this is a computationally very cheap method to use. It can run it on a desktop, so long as you have ensemble forecasts that have already been produced. And so all the things that we do are based on operational ensemble guidance, and so it's something very straightforward to run on a single processor computer. Next slide, please. So let me talk about what we use for the forecast metric and the fields for this particular product. This is an example of Hurricane Dorian's forecast from 2019. And so our first iteration of this technique, if you want to click it next, it used the distance along the major axis of these position ellipses, which was actually one of the early HFIP product developments. And so this varies by forecast lead times. Here we transition from a long track, mainly a long track variability early on, to a cross track variability later in the forecast. And so the nice thing here is that it describes the position variability in the direction where the position variability is the greatest. However, the disadvantage here is that that direction changes from lead time to lead time. And so that may require looking at sensitivity output for multiple different times, because the sensitive area could change. In an operationally constrained environment, that's not very useful because the Hurricane Center forecasters don't have a lot of time to look at this. And so if you go to the next slide, what we did was we developed a time-integrated track variability, which is based on doing the EOF decomposition of the ensemble latitude and longitude positions across the entire 120-hour forecast. If you want to click on that, please. It's just a statistical decomposition of the track, and what you get from that is a perturbation track forecast relative to the ensemble mean that is consistent with explaining the most variance in the track forecasts. So in this particular case, the perturbation track forecast, the representative perturbation track forecast, is something that is slower and recurves earlier than the ensemble mean track. So the perturbation is in the dash and the mean track is in the black. So the nice thing about this approach is that it's a really elegant way of dealing with the autocorrelation and track. And it allows the forecaster to do sensitivity calculations for one time rather than having to repeat it over many, many times. And so we developed an operational product based on that. So you're going to go to the next slide, please. Then the other thing that we had to deal with is how do we represent the steering flow? So this is the ensemble mean 300 to 850 hectopascal steering flow for this particular time for a potential flight track. The storm is at the black dot there, the vectors of the steering flow. And what you see there is that the steering flow very clearly includes the vortex there. And so if we want to look at steering, we've got to get rid of the vortex somehow. And so to do that, if you want to click there. Yeah, next slide, please. We had to somehow remove the TC vortex. And so to do that, if you want to click the next slide, please. We use the Galarno and Davis vortex removal process that separates the wind into a TC wind and an environmental wind based on the vorticity and divergence associated with the TC. Once we get the TC's vorticity and divergence, we do an inversion process to get its winds, and that's what's shown here. This is the TC winds associated with the vorticity and divergence, and then we can subtract it from the total wind to get the environmental wind. And so if you go to the next slide, please. This is back to that total wind, and if we subtract out the vortex, go to the next slide. Here's what's left over, and this is our environmental wind. And so we do this for each ensemble member steering wind at each individual time. We subtract the TC, and then we can compute sensitivity. And the nice thing about that is it removes the effect of the vortex. So if you go to the next slide, please. Once we have the steering wind and the track forecast, we can compute a sensitivity field, which is in the color shading here. Here, the warm colors represent regions where if I increase the steering wind in the southwest to northeast direction, I'm going to get a storm that is more to the northeast in the subsequent forecast. And the cold colors are the opposite. The dot here represents where the TC is predicted to be at this time. And so here we have sensitive region really right around the storm and then extending out to the northeast in a weakness of the subtropical ridge. And if you go to the next slide, click that, right, that's the explanation. Go to the next slide, please. The pluses are where the dropsondes were deployed based on this forecast guidance. And so in this case, there were 2 circumnavigations of the storm done by the G4, plus some extra dropsondes to the northeast in the weakness in the subtropical ridge. So what you really want to do is to have the plane target the regions that are indicative of the most sense, where you get the biggest change in the track forecast given the steering flow. And that's what this gives. Go to the next slide, please. So this is just a little bit of summary on the real-time application that was officially done for the JHT project from 2019 to 2021. There were 55 flights for 16 storms. Subsequently, in 2022 and 2023, I've continued to support this after the end of the JHT project and transitioning to a hurricane ocean test bed. And during that time, there's been 30 potential flights done. This past season, NHCs actually did a lot of the flight planning themselves without my input, which was really nice to see based on this methodology. Ran it for all storms starting in 2020. We can compute sensitivity from both ECMWF and GEFS ensemble input using the same Python-based software package. And it also provides input grids to the NHC software that they use to develop flight tracks. So if you go to the next slide, I'm going to show some examples from that 2019 to 2021 period. These are the gray lines are best tracks of storms that had G4 flights. Dots were where the G4 flight took place. And on the right, you see the names of the storms and how many flights there were. Orion's the biggest number, but there's a good mix of storms in here that I'm going to show some examples of in a second. Next slide, please. So here's a couple of examples of Fred from 2021, Ida from that same year. Again, storm is at the center of the plots, and then you've got 300-kilometer range rings on this. And so in this case, both Ida and Fred, I grouped them together because these are examples of storms that are very sensitive to the near storm steering flow at the time of sampling and out to the northeast. A common theme that we saw during these 3 years is a lot of sensitivity to what's near the storm and to how strong the subtropical ridge is to the northeast of the storm. Next slide, please. Here left is Hurricane Laura. Again, another example where the track forecast is sensitive to the subtropical ridge to the north and the east of the storm. And the figure on the right is for Hurricane Eta, when it's in the southwestern Caribbean Sea. Here you've got sensitivity more to the north of the storm in association with how close a upper level trough gets to the storm as it's moving into the Gulf of Mexico. Next slide, please. So it's nice to look at into some individual case-by-case basis, but I wanted to do is look at all of the cases where G4 flights were done during that 2019 to 2021 period, and compute a bit of a sensitivity climatology. So what you're seeing in these two figures is the sensitivity averaged in a storm relative framework for all 55 of those cases from 2019 to 2021. In two different frameworks, the figure on the left is for the wind component of the steering flow, whereas the figure on the right is the vorticity of the steering flow. And so the darker the colors, the greater the sensitivity. And what I've done hopefully you can see there's two lime green circles in there. One of them is a radius at 1.5 degrees, which represents the inner circumnav that's done by the G4. And the outer circle is a 3-degree circumnavigation. So that's the outer radius that's done. And so what we see for the 55 cases from 2019 to 2021 is that in terms of the steering wind, the largest sensitivity is generally to the right or to the east of the storm, maximized between 300 to 600 kilometers. But also within the storm itself. And so generally speaking, the two circumnavigations are doing a pretty good job, though on a case-by-case basis, it's good to go out to the east, at least for this set of cases. If you look at it in a steering flow vorticity perspective, which is on the right, you see that again, that okay, good. On the right, you see that the sensitive region is, in terms of vorticity, is again out to 600 to 900 kilometers and a little bit to the south. So, yeah, it's just an interesting pattern. I think it reinforces the idea of the strength of the subtropical ridge as being an important contributor to the track variability, at least during this period. What I will say is what you didn't see during a lot of those periods is a lot of upstream sensitivity in the mid-latitudes. There were only one case out of all of these where we saw upstream sensitivity to mid-latitude features, and that was in Hurricane Zeta. Next slide, please. So again, I said that we continued this into 2022 and 2023. This is just a couple of examples. Ian, on the left side, a lot of sensitivity again to the strength of the subtropical ridge to its north, and Idalia as well. Again, sensitivity to the subtropical ridge to its east and the trough to its northwest. And I'll be talking a bit more about Ian on Thursday when I talk about more of the hot related work. Next slide, please. So just to summarize up, this method is a pretty computationally expensive and flexible method for estimating forecast sensitivity. The EOF decomposition of the tracks has turned out to be very efficient choice for doing track forecast sensitivity. It's very easy to explain, and it makes it straightforward for the forecasters to use. Most of the position forecast sensitivity appears to be in the near storm steering flow and into the strength of the subtropical ridge to its east. Very few cases of far upstream sensitivity. And on Thursday, I'll be talking about some of the newer developments in terms of forecast sensitivity, looking at more hazards forecast sensitivity. So I encourage you to stick around for that, and I'll be happy to take questions later on.
All right, we're on to our next speaker, Xingren Wu from EMC. We'll be discussing aircraft observation data impact on GFS forecasting skill of the North Atlantic tropical cyclones.
Thank you. Can you hear from me?
Yes, we can.
Great, thank you. I have two parts of presentation. The first part is for the aircraft observation data, and the second part is windborne data. And I want to acknowledge my colleagues Vijay from EMC and their collaborators, Jen, Jiayi, Jason, and Ryan. Next slide. Outline, I'm going to talk briefly the data experiment setup, followed by results of TC track intensity and minimum center pressure, and then a brief summary. Next. For the experiment periods, it covered from August 20 to September 17 for this study. The control experiment is from GFS operation, which assimilate drop zone and flat level high density observation data. For the denial experiment, the drop zone and the HD ops data are excluded from the simulation. So the difference between the experiment is going to reflect the TC Recon data impact on GFS TC forecast. Next one. The model we used is GFS version 16. For both DA and forecast, we run the system 4 cycles per day, and the forecast length is 180 hours. I think everybody is familiar with GFS, so I'm going to skip the details on it. Next slide. For the track, the left panel shows the track scale. Black color shows the track scale from the denial experiment, and the reference is from GFS operation, which is shown in green color. Red panel shows track error. So we can see that the track scale is higher from the denial experiment over most of the time, with a lead time of 12 to 30 hours and 60 to 132 hours. The improvement varies between 3 and 12%. And during the same time, the track error is smaller. Next slide. This is the intensity. Left panel again shows the scale, and the red panel shows the Vmax error. And we can see the scale is higher in the denial experiment, also for the track and for the intensity, and the error is smaller in the denial experiment, which indicates a negative impact for the TC Recon data for over this period. Next slide. So in this slide, we show a different analysis. So this is a track over the cycles which only cover the TC Recon data. And this period covers the Hurricane Franklin, Harold, Adelia, and Lee. And only when the Recon data is available, the cycle was included in this analysis. As you can see that the track error changed from all the cases from forecast 38 hours to 168 hours. The track error becomes smaller in the denial experiment, which reflects is more positive than negative impact of the TC Recon data. Next slide. This is the same analysis over the cycles with TC Recon data only for the intensity. Left panel shows track scale, and the right panel shows Vmax error. The intensity scale doesn't change. It's similar to the one with all the cyclones considered. So it still shows a higher intensity scale in the denial experiment than in the GFS operation. Next slide. This is shows the minimum center pressure in the left panel. As we can see that the black color, the denial case, the arrow is smaller in the denial case than in the GFS operation, which indicate a negative impact of TC Recon data. Next slide. So to summarize, when all the storms are considered for the case selected, the impact of Recon data, this includes both drop sound and HD ops, seem to be negative for track and intensity forecast. These results are different from the case we studied over 2020 and 2021 case. So the drop sounds and HD ops provide a more positive than negative impact. But the direct impact of TC Recon data on the track forecast is neutral to positive when we only consider the cycles with the TC Recon data available. Even so, it still shows negative for intensity on the minimum center pressure impact. We have all heard about the GFS doesn't perform very well this year. So this might be something we need to look into more details. Next slide. The second part of my presentation is windborne observation data impact on GFS forecasting skills over the tropical cyclones. I want to acknowledge my course visit again from EMC, Todd and Joanne from Windborne Systems, and the collaborators, Daryl, Emily, Andrew, Jiayi, and Michael. Next slide. The global sounding balloon is a highly cost-effective platform. It supplements existing collection measures and closes existing in situ data gap as it can reach data sparse region. It collects in situ observations from the surface to the stratosphere for the super-orbit wind sensible temperature and specific humidity. The slide shows the balloon tracks over North Atlantic from August 6 to October 9, 2022. And this is a period for this study. Next slide. For the control experiment, we use the same sighting as GFS operation, that it is there is no windborne data assimilated. For the windborne data experiment, we added the windborne data which was provided with private buffer file from windborne system into GFS DA GSI assimilation. We run 4 cycles per day for DA and the forecast again. The model forecast length is 240 hours or 10 days. We examined the whole impact on the GFS forecast, but for this particular presentation, we focus on the TC forecast over North Atlantic and East and West Pac. Next slide. This is a track. Left panel shows the scale and the right panel shows the arrow for all the storms over the period August 6 to October 19, 2022. Black color shows windborne DA and red color shows the control. As we can see, the windborne DA shows higher track scales and lower track arrows. The improvement is about 13 to 17%, in particular over the period from lead time 42 to 156 hours. Next slide. This is intensity. The difference fluctuate between positive and negative for the scale, which is shown in the left panel, which indicate there's no clear impact either positive or negative. Next slide. This is a East Pac track, left panel the scale and right panel intensity. With short lead time from hour 12 to 78 hours, it clearly shown the positive impact or higher track scale in windborne DA experiment. From 84 to 120 hours, it shows slightly negative, but the sample size is very small. Next slide. This is intensity scale on the left and the arrow on the right. For the short lead, between 12 and 60 hours, the scale is higher in wind-borne DA, and with long lead, with lead longer than 60 hours, the intensity scale is lower in the wind-borne DA. So again, for intensity, there's no clear signal for the wind-borne DA impact. Next slide. This is a Westpac. As we can see that there's a positive impact or higher scale in wind-borne DA track scale in the left panel, in particular over the period from 84 hours to 162 hours. And with a short lead between 0 and 72, it fluctuates between the positive and negative with small difference. Next slide. This shows the intensity. Left panel again is scale, and right panel the Remax arrow. It's mostly positive impact from wind-borne, as the intensity scale is higher in wind-borne DA, except for the lead hour 144. Next slide. This is a single case forecast from September 17, 2022 for Fiona. Left panel shows a track, black color, the best track, control in red color, and wind-borne DA in blue color. As you can see, the track forecast is improved in the wind-borne DA clearly. Middle panel shows intensity. The difference between red and blue color is small, but in general, it shows improvement in the wind-borne DA, which is in blue color. Red panel shows central pressure, a similar positive impact for the minimum center pressure, in particular with long lead. Next slide. So although we focus on TC forecast, I just want to show in this slide, in general, wind-borne DA shows improvement over North Atlantic. The left panel shows the RMS. Top left shows the geopotential height RMS, and bottom left shows wind RMS. The middle panel shows RMS difference between wind-borne DA and the control. One color shows positive value, which means wind-borne DA has a higher RMS, and the cold color of blue, which means the wind-borne DA has lower RMS. As we can see that in general, from 42 hours onward, there's a clear improvement with wind-borne DA or RMS reduction. In particular, the reduction is over 200 hectopascal. Next. So we can see that the difference between the wind-borne DA and control over 200 hectopascal with a lead time of 168 hours and 216, or day 7 to day 9. The difference is statistically significant at 95% level. Next slide. To summarize, wind-borne observation data helped improve GFS forecast over the North Atlantic region. The wind-borne observation has a positive impact on GFS forecast for tropical cyclone tracks. For the future plan, we would conduct more data impact experiments using wind-borne data collected in 2023. Thank you.
All right, thank you very much. Brings up our last speaker for the session. It's going to be Jason Sippel and Lisa Bucci, using UAS to improve tropical cyclone prediction and review and path forward.
You get me again. So this is motivated by the substantial increase in capacity in UAS that's ongoing. The OER has a UXS office, and we get notices a lot about the new systems coming online, and there's a lot of new capabilities. Joe Sion's in the room. He has SUAS that they're making headlines, launching them for the P3, but there's also new capabilities in terms of larger UAS. Xingren just talked about the balloons and the impact they had on the forecast. So we need to stay ahead of this. That was kind of what motivated this talk, to get this to a larger audience and get the gears turning. So I'm going to talk first about the impacts, and then Lisa will talk about some ConOps thoughts. So I talked about motivation, and really the end goal in the motivation is right here. Seamless integration of crewed and uncrewed systems to maximize the benefit of TC forecasts. Kind of go back to the Global Hawk right here, but we have, I think this is the Altius. And then, of course, we want to work this in with the crewed systems. So I'm going to talk first about motivation. I talked about motivation, but I'll talk about recent work, and then Lisa's going to talk about challenges and ConOps. So a little bit more about the motivation. A big one is that we have gaps for crewed systems. So this is all the NOAA and Air Force task missions from this past year. That's a lot. We have great coverage here in the Southwest Atlantic. Out in the MDR to about 55 west. A lot of years, like if we have systems down here in the Caribbean, we have great coverage through here. We get great coverage in the Gulf when we have systems in the Gulf. Where are our holes? Well, a big one is out in the MDR, east of about 55. It is a lot of work to get the planes from Lakeland or Biloxi forward deployed down to the islands, and then tasking systems out here. And you have to start thinking almost a week ahead of time. And the Air Force, I think they don't go further east than about 55. NOAA can, but it's just hard to get out there. So we have this hole out here, and we have this, we have situations where the planes get on systems out here just a couple days before they're in the islands. And so that's kind of a big hole. Down here in the Southern Caribbean, way down here, that's a hard area to reach. Would be helpful to have more capabilities down here. And then of course the East Pac, we saw the example with Otis. There's other examples, but considering the amount of activity out here, that's not very many flights. So there's holes spatially. There's also holes vertically. So this is an example of observations. Altitude led this paper. This was from Hurricane Maria, and we've got all kinds of observations here. I've got TDR, got flight. Let's see, AMVs up here. So this is height by radius, and then this is just by radius. We have SONs here in green, flight level data. And down here in the boundary layer, yeah, we have some SONs and we have some SFMR, but we don't have a lot of data in the boundary layer. It is a big hole. We can't fly down there because it's not safe. So best option, really, we could get some retrieve winds from various instruments, but really another very good option for in situ data is SUAS. And we have some fascinating results from the Coyote data, and we have some more cases from this year that Joe brought us. So that's very interesting, an interesting development in the science. So going back to 2016 with Shout, we used the Global Hawk. We collaborated with NASA, and we flew a bunch of patterns over the Atlantic. It could go for 24 hours, maximum duration. We flew a bunch of storm-centered patterns for various storms out in the MDR and in some cases closer to home. And we ran, INSEP EMC ran GFS with and without the Global Hawk data. With is in red, without is in black, and you can see that it improved the GFS forecasts a lot. And it's kind of similar to Windborne, a big substantial 10 to 15% improvement in track skill. That actually spurred EMC to allow the Global Hawk into GFS in 2017, and then we stopped having Global Hawk. So you fast forward to 2022, you just saw the Windborne results. Here's all the tracks over the Atlantic. Great, fantastic results. No balloons is in red, with balloons is in black here. Much lower track errors. Great result, great data all the way up to the stratosphere. What this gives us, I've looked at the profiles of data. I'm not sure if he showed it or not, but it fills in a major gap in the winds. We don't get mid-level winds out in the Atlantic, out over the MDR, anywhere. We have satellite radiances for thermo. It's not as good as in situ, but it helps, right? But we don't have winds, right? And we need something. So this fills a major gap, and it would be great if we could have more of this. And as he showed, it's not just improvements to TC track, but we saw large-scale improvements too from this data. From SOES, I did some work with Altu and Catherine Selwood, and we assimilated this data into the operational HWRF. So here's from Maria. Here's some of the cases going around the eye. These were all eye wall releases, and we ran HWRF with and without the data. And that's here. So with the coyote is in red. So this is error on the top for track, Vmax, Pmin. Without is in black. Then with the skill, it's kind of easier to see with the skill, but we had some good improvements with track skill. Also with Pmin, not as good with Vmax, although it's generally more positive than negative. So again, this is another demonstration of impacts, positive impacts with UAS, in this case, SUAS in the inner core. And we saw similar improvements with Ian. We looked at Ian with HAFS and we assimilated the SUAS data. And even though it was a Category 5 hurricane, we saw track improvements assimilating the data. And I think that takes us to Lisa. There you are.
Thanks. So when Jason and I were having these conversations, he was asking me these questions about when do forecasters have the most challenges when planning operational taskings. And one of them he highlighted really well. It's those storms that are approaching the Lesser Antilles and the Windward Islands. We had Elsa in recent history that strengthened a lot more than we were expecting it to, and it hit Barbados. Barbados wasn't very happy about that. So having information out in front of these storms approaching the islands would be particularly helpful, but we do have challenges getting there. Like Jason said, it's hard to get all those crew members out into the islands, and the logistics involved in it, it's pretty complicated if you've asked anybody who's planned the hurricane field programs. Again, I had shown this image on the right. We only got one flight into Otis. We have a huge data gap in the East Pacific. It's kind of a little bit sad that I was happy that we got 5 missions into Hillary when you looked at all the missions that we got into Adalia. So you have the problem of not having any places that you can really operate out of on that side of the coast for resource purposes and also safety issues. But you also have these storms that are coming near these mountainous terrains, and that's really not a safe situation for our aircraft, our crew members. They're experiencing a lot of mountain turbulence, and we don't want to put them in danger. So a reason for exploring UAS options. Also, so the way that our ConOps works, we often are not getting missions at night. So those overnight hours have gaps, and a lot of times we'll get these packages that are coming out first thing in the morning on the East Coast. It's the data that everybody is reporting on in the morning, and they're not, we're not basing a lot of that information on aircraft observations. And finally, and you probably saw this recently in the news, but it's happened before, where you'll get, for whatever reason, you'll miss missions. It happens. You know, we've had everything from birds to broken aircraft to COVID. So missions get missed. It would be nice to have options to back up these critical ConOps situations. So how would we potentially look at future ConOps if we were kind of looking at all of these UAS options? So right now we have this a setup where, you know, we have a disturbance And from there, through landfall or extratropical transition, we are starting to plan missions, either with the Air Force or with NOAA. And we are blending those two research and operational goals to kind of be able to go get those observations. But if we're looking at maybe adding in this third row, this UAS row at the bottom, there's the potential where we could have UASs that are constantly out there patrolling, similar to the days when they used to patrol the MDR way back when. This could be then when a disturbance is starting to form, we start to deploy swarms, more of them, to go towards the area and constantly collect data. When it's too hard to start getting all of those manned missions into a disturbance. And then once that disturbance starts to form into a tropical storm, starts to becoming more of a land threat, we could be doing what we do now, getting our heavy aircraft in there, getting our crewed systems that have more observing systems attached to them. Whereas maybe a UAS doesn't carry as many options, we now flux and have something bigger. And then fill in the gaps, like Jason was saying, where we're getting the boundary layer observations or the nighttime hours that still have issues. And finally, we have this backup during the critical landfall situations. Or we transition away. It's not becoming as much of a threat to land, but maybe we have need for extratropical taskings. And again, then the UAS could start taking over at this point. So these are just some ideas of how we could begin to think about integrating UAS into our future CONOPS. And again, we're looking at hitting these goals of extending our geographic coverage, having consistent observations temporally. And Jamie mentioned this at the beginning of the day, it's been mentioned several times, but enhancing that surface wind field analysis, getting a better idea of the structure so that we can better communicate the hazards. And finally, we've shown all these modeling results. A lot of this could be improved by increased measurements in the vertical and co-located wind and thermodynamic measurements taken in situ. So those are just some things to consider. They could look like a lot of different iterations of them. We could be blending a lot of different UAS platforms. They could be single use and low cost, or long duration with multi-sensors. And obviously we could be looking at the differences between buying the data or a NOAA operated platform, or a blend of both. And as is always important, we would have to be keeping on top of this so that we can update our safety procedures, because if we have more players in the storm, there's a huge need to be keeping our safety procedures up to date. So we could expect an increase in participation in the NHAP. So, Jason's talked a lot about the value and the proof of concepts in future UAS operations. On the operational side, we have a need for increased coverage. And the best approach, it seems, is if we could take this blended approach somehow of taking manned aircraft and supplementing them with uncrewed missions, and using a variety of different instrumentation to fill the need as the TC life cycle evolves. That will end it here. Thank you.
All right, we have opportunity now for discussion. Andy.
This question is mainly for Jason, kind of your first talk, a little bit the last one too, but so in light of the results you show with, notable improvement, pretty much, especially in HAFS, anytime we get aircraft data in there, what would you say is the next step to utilize that information? Does it mean more flights, further optimizing like that cycling, how we use it, all of the above? What's your take on that?
Yeah, I talked to Eric and he agreed, we're going to start tasking, when things come off Cape Verde, right? I mean, yeah, I don't, we're stretched thin, right? on the flights. And I don't, it'd be great to have more. I don't know how feasible that is. I know that like Lisa said, the islands want stuff sooner, but I think we need a serious investment in the UAS. That's kind of why we ended with stock, is we need to start thinking about these holes and how to address these challenges to get some data in areas where we don't have it. And as far as the next step in HAFS, more immediately than, because the US is kind of a really big problem. I think, another big thing we need to do is really start using the satellite data better, which we're not right now, especially in HAFS. So I think, we're going to have a combination of those two things to fill in some of these gaps. I don't want to talk anymore. I don't know, other people need to talk.
Thank you. Question from Pete Black about why not deploy to Mexico. Here's Lisa.
So I can answer this question, and I'm sure if we have any folk from AOC, they could jump on as well. But they've done evaluations of those cities. They used to be able to operate out of them. They don't have the equipment. They don't have the runway lengths that we need to operate out of those cities. They might not have some of the parts or the nitrogen that you would need to have missions in them. So they have been, and then some of them, they're just not safe to operate out of anymore. Like the State Department's like, yeah, you should probably not do that. So it's not an option. They recently looked at La Paz, that got taken off the table from AOC. So it's just, there's not a lot of places that we can work out of. We can work out of Costa Rica or San Diego, and that leaves the entire Mexican coastline completely open.
Yeah, it's another question for Jason. So really interesting, the idea about the cycling at the lower thresholds, improving the forecast. So I had sort of two-part question. Should we look at lowering that threshold for HAFS A to 40? And then also, should we consider lowering the thresholds from both of them even lower than 40?
Yeah, so I know EMC did run HAFS A with a lower threshold this summer, and I think Zach said they tested it, and there was some improvement, taking it down to 40. I would say, yeah, I was thinking about next year, how to deal with this and also have some diversity. Maybe do HAFS A at 40 and HAFS B at 30. I think we should definitely, at least one of the models should be lower than 40. One thing, sorry. I don't think it's universal that keeping like HAFS B at 30, for example, is necessarily always better, right? I think it's situationally dependent. Likely, and I'll give you an example. So GFS has a better DA system than HAFS, right? I mean, it's just more mature. They're bringing in all sky. We're not, right? So I think in a lot of cases, using GFS as a first guess is probably the better thing to do, right? At the weaker intensities. But we have this situation where it looks like, okay, when we have this intercore data, maybe that it's not the best thing to do. So I don't know how to solve that, but maybe we really got to start thinking about how to do things like this adaptively. So.
Yeah, I was just going to mention that there is a notable data gap in the Eastern Atlantic, and I was involved in Shout, and the Global Hawk was a really great solution to that. At least my understanding is that they no longer use the Global Hawk because it was cost prohibitive, but it did fill some of those gaps in both location and also the dropsons being launched from the stratosphere gives you those full, basically full tropospheric profile. And I'm just wondering if there are any other unmanned systems that anyone can think of that can either help provide for the East Pacific or the far Eastern Atlantic to help fill that gap for less cost.
The answer is yes. Is John Walker on? Because he could speak about it.
Jason, can you hear me?
Yeah. Go take the floor, man. You know all the details of this stuff.
Sure. And just so you know, I'm joined by Brian as well, the director of the UXS Research Transition Office. So, yep, this is something we've been looking into very, very closely, and speaking with different manufacturers, different producers of high-altitude, long-endurance UAS. Long story short, yes, we're looking at trying to recapture all the benefits from Global Hawk at a much, much reduced cost. Lisa mentioned potential data buy options. There's a company we're looking at that's developing a platform. They've already tested it. They're looking to test the extended ranges of it, but the goal is to launch it and get it to fly within the stratosphere for up to 6 months at a time. Their operational price point, once they get to that point, would be about $250 per flight hour. So do the math, figure out what the best ConOps would be. This is something that we're just looking into at this point.
So, okay, the previous talks tell us to get more data DA in our system, either global or regional, we get a better track intensity. So I want to ask Jason, what about the structure? Do we get the right size of the storm? It's a positive bias or negative bias for the...
Excellent question. So I was just involved with a FY18 supplemental project with Sarah Ditchick. We looked at 4 years of evaluating the impact of, it was just dropson data in the basin scale HFIP. And actually, the biggest impact from the dropsons was on the outer wind radii, R34 and R50. It had very significant, I don't want to say statistically significant, but very large improvements in those, and very consistent across the sample. I did some work when we added the HDOB data and some extra SONs in the GFS 16. And I also saw some improvements in the outer wind radii. We didn't necessarily focus on that in the paper because the biggest impact was on the track improvement. Yeah, we've seen improvements in structure. So I think that's we need to be thinking more about those things. Yeah, that's what I said. It was for the SONs.
One color, right? For your HAFS A and B, R34.
So right, okay. So you're talking about the HAFS results, right? So the HAFS results are preliminary. I don't know about. I wasn't necessarily focused as much on the structure. The HWRF, what I'm talking about with the SONs, that was a much larger sample. We looked at our direct impact. It had over 400 cases in it, and it was 4 years of storms. So this was just a few storms this year. So this is preliminary. That's, I would say, much more solid.
I have a question for Ryan. So Ryan, when you look at the sensitivity or the GEFS versus ECMWF, do you see a lot of times very significant differences, or is it fairly similar in most cases?
Good question, Chris. I would say most cases they're pretty similar. The caveat being, I don't think you can make a very fair comparison between the GFS and ECMWF until after the upgrade that took place in September of 2020. Because after that, the forecasts after that point are far more skillful in terms of the track variability. And so for the limited cases that we have since then, there is general overlap of the areas. Again, I think the GFS shows a lot of weaknesses in the subtropical ridge to the east, but not perfect overlap. And some of that is in what is the direction of the track variability in the GFS versus the ECMWF. They don't always overlap perfectly. But I would say more often than not, there's a lot of overlap between the GFS and the ECMWF.
Okay, thank you. More questions?
I like how we keep talking about data gaps, and I haven't heard much on better utilization of satellite data. We do have satellite data out there, but I like simplistic. And when I see a lot of these statistics, just a suggestion besides what I mentioned with stratification, the simplistic stat of FSP, frequency of superior performance, which I know most of you are interested in, because when you average all the errors, it's just see how consistent, these results are. Because especially in smaller samples, a few bad ones can totally skew it. A few good ones can totally skew it. And just to see how often one is really better than the other. I know the consistency metric tries to address that, but just I'd love to see more of those, that particular chart, the FSP, just suggestion.
Hey,
Any
Pete,
comment?
it looks like you have your hand up.
Yeah, thanks, Lisa. I just had another thought listening to my old buddy John Walker talking and thinking about my new colleague here, Todd Hutchison with Winborn. How about you guys get together and organize a joint deployment of a Global Hawk, maybe a mini Global Hawk type system in an area like the Eastern Atlantic, together with a cluster of windborne balloons, so that you could create a movable array of sounding data.
Yeah, hey Pete, thanks. I think that wouldn't be a bad idea. All options are on the table. All certainly things we're looking into. It really just comes down to any interest or pull from our stakeholder partners, NHC, AOML, and across the rest of the agency. But certainly.
Thanks, Pete and John. This is Todd from Winborn. I just wanted to throw in one piece of information about next season, 2024. Our current plans are to set up again in Cabo Verde, actually this winter, to have launches about 3 to 4 times per week over the winter, but then to ramp up to probably as many as 10 per week, but probably on average more like 5 to 8 per week during the summer, next summer. So there'll be more opportunity to explore the value of the observations next summer, and hopefully we can see what kind of holes we can cover out there. But I think we should be able to get pretty good broad coverage in that area.
Are there any other questions?
All right, I think we're probably good for today, considering everybody looks like they're burned out and falling asleep. Just prepare yourselves, because tomorrow is going to be longer, and Thursday even longer than that. I would like to welcome you all to come back tomorrow, whether that be online or in person. Tomorrow's sessions will start off with HAFS implementation, talking about the IOC of current HAFS, as well as real-time experiments that were done this summer, and the more detail on the HERC, the HAFS in the cloud. We'll then have HFIP R2O and O2R talks, and then finish out the morning, or excuse me, finish out the day with sessions on hurricane observations panel from various NOAA offices and outside NOAA offices, and DA and impacts from DA, followed by our closeout session that goes from 5 to 6 p.m., hosted by Daryl Kleist, focused on DA discussion and lessons learned. So have a good night. Thank you all for coming.